unit is both kinetics and equilibrium, but today we're going to start talking about kinetics, so how fast things go. We need to remember what kinetic energy is as well as temperature. So kinetic energy is the result of the random movement of particles. It's the energy dealing with velocity specifically, or movement. And temperature is a measure of the average kinetic energy of the particles in a sample. So not all particles are going to have the same kinetic energy. We're going to see that here in a sec. But if we add in thermal energy, we increase the average kinetic energy of the sample, and thus we see an increase in the temperature. Okay, so here is a mastery check question for you to complete using Google Forms. You'll have two others that go with this Google form in a sec, so you can come back and do this. Okay, let's talk about this, our Maxwell-Boltzmann curve. So this is a graphic representation of the values of kinetic energy versus the whole sample. So go ahead and draw your x and y axis. On the x-axis will be kinetic energy, and on the y-axis you'll have the number of particles or the proportion of particles with a given kinetic energy. So here's what a Maxwell-Boltzmann distribution will look like initially, okay? So a couple points to know. Notice that at zero kinetic energy, there are zero particles, because zero kinetic energy would be absolute zero, where all molecular motion stops. And we have, well, it's kind of a bell, kind of a ski slope. Notice it's not symmetrical. And so you'll always see kind of this tilt as you get to higher kinetic energy. So a more uniform steepness on the low end of kinetic energy, and then kind of this swoosh, and it goes out ultimately to infinity. You've got a little asymptote here. Okay, so we're going to say that this blue line is temperature 1, and if you have a second colored pencil or something, you might want to use this. So your average kinetic energy splits the area under the curve. So the area under this curve is equal to the area under this curve. So it's not just straight at the peak necessarily. That would be true if it was a perfect little bell curve, but it's not symmetric. Okay, so what happens if we have maybe a higher temperature? Well, our curve's going to look a little bit different. It'll look like this. So as temperature increases, we're still going to start at 0 at the origin, and it's still going to be a little bit lopsided, but our curves will get shorter and broader. Okay, so here our second temperature is higher. The midway point, the average, is higher than the first one. So our second temperature is higher than our first. Okay, now for both of these, and this, you'd only be asked to sketch these, so a very rough sketch. But by the way, the number of particles under the curve, the area under the curve, is constant between those two. Okay, because we're not randomly losing matter or gaining it. You know, that kind of breaks a big rule. Okay, so what if we had a sample at an even higher temperature? Well, we would have a shorter and even broader curve. But again, notice they all start at the origin, and they're all kind of lopsided. Okay, so you can practice it, and if you're not so artistically challenged, you might accidentally wind up on something that's easy to draw for you. Okay, let's get back to chemistry, and you're going to see those Maxwell-Boltzmann distributions throughout. So effective collisions, because molecules have to collide in order to react. And so we're talking about the rate of reaction. So how do we get those reactions? The molecules collide. They have to have adequate energy and correct orientation. So let's talk about what those mean. Adequate energy. Only collisions with enough energy to react are going to form products. So not every collision is successful. And you can think about it as you kind of have this little hill to go over. So if you're getting this boulder from A to B, yeah, hey, look, that's an exothermic reaction. There's a net loss of energy, but you have to get it over this hump. So what is that hump? Well, it's called the activation energy, and it's the energy required to form the transition state. So when molecules collide and react, there's this very high energy, temporary, fleeting moment transition state up here that's very unstable. And then it's going to react to something that's more stable to form products. And this is true whether it's an endothermic or exothermic reaction. Okay, now the value of activation energy varies greatly from one reaction to another, and the magnitude of this value plays an important part in determining the overall rate of reaction. Okay, something with a very high activation energy is going to be slower because fewer molecules will have enough energy to react. Okay. You could also think about this in terms of a Maxwell-Boltzmann distribution. Okay, so you've got your high temperature, your lower temperature. Notice that there's a lot more area under the purple curve that is above this activation energy point. So a greater proportion of the molecules have sufficient energy, which means we get a faster reaction rate out. Okay, the geometry of the collision. So notice there's only one way for these two molecules to collide. All the other collisions, the molecules are just going to bounce off of each other. So here's another version. This is hydroxide and hydronium, OH and H3O. And notice there's only one way for these two to hit and break into two waters. Okay, now here's the thing. There's two parts of an effective collision. There's energy and orientation. Which one of those two, or can we change both? Which ones can we affect? Well, the answer is one. We can't do anything to change the orientation of those molecules and how they collide. Remember, there's a lot of random motion happening. But we can change the energy of the collisions, and we can change how many collisions are happening. So that's where we're going to talk about factors affecting rate. Okay, so here's our factors: temperature, concentration, particle size, pressure, and catalyst. You need to be able to account for each one of these and why it affects the rate. So is it affecting the number of collisions? Is it affecting, or not the number of collisions, the frequency of collisions, the number of collisions per unit time? Or is it affecting the success rate of those collisions by having more collisions with sufficient energy? So those are your two things you need to be able to explain. Let's delve in. Temperature. Okay, temperature is the easiest way to speed up a reaction. Okay, the rule of thumb is that a 10-degree increase in temperature, 10 degrees Celsius or Kelvin, doubles your reaction rate. And here's why. It increases the number of collisions per unit time. In other words, it increases the frequency of collisions because all those particles are moving at greater speed. And two, it increases the proportion of collisions with sufficient energy. So if here's our activation energy, again, we just saw this, but at higher temperature, we have a greater proportion with sufficient energy. Number two, concentration. This is molarity, or moles per cubic decimeter. So an increased concentration increases the number of collisions per unit time, or the frequency of the collisions. Don't just say that it increases the number of collisions, because it doesn't do that. It increases how many are happening per second or minute, so the frequency. You can think about it this way. Here at very high concentration, well, it's crowded. These molecules are going to run into each other a lot more. And the rate is going to decrease as the number of particles decrease, just simply because they're not going to run into each other as much. Okay, particle size. Here we're talking about surface area. So if we decrease the particle size, say we crush or grind up a solid, something like that, we increase the number of collisions per unit time. We increase the frequency. Again, we don't make them more successful, we just have a sheer number of collisions that are happening each minute. We have a greater number. Okay. So if we have a big chunk of something, well, these little red guys can only hit what's on the exterior and collide with that. But if we crush it up, now there's a lot more space for these red particles to collide with the green. So we get a much faster reaction. Okay, pressure. This only affects gases, and remember, if we increase pressure, we decrease the volume, and if we decrease the volume, the cubic decimeters, we've increased the concentration of the reactants. So pressure works the same as concentration. It increases the frequency of collisions. Okay, and lastly, catalyst. These lower the activation energy so that a greater proportion of collisions have sufficient energy. Okay, so you can look at this little graph. Here's our energy profile. Or you could look at it on a Maxwell-Boltzmann. Okay, it's the same curve, the same temperature, but notice if we lower that activation energy, if we back that up, how much more of the curve now has sufficient energy. So catalysts are also very effective. All right, here's your other 2 questions for your mastery check. So you're going to answer those using Google Forms, and we'll go on from there.